Welcome to the PluTech channel. Today we have a topic to discuss about DeepMind and UC Berkeley unlocking the ultimate computing power in AI. Don't miss the chance to join us and share your opinions with us. The high costs and low speed of training large language models, LLMs, have generated an ongoing debate about the possibility of improving the performance of these models by investing more computational resources during inference, without the need for new training. In this context, a new study led by researchers at DeepMind and the University of California, Berkeley, explores ways to improve the performance of LLMs through strategic allocation of computational resources during inference. The results, presented in a recent paper, indicate that optimized use of compute during this phase can yield significant performance gains, eliminating the need for larger models or extensive pre-training. Until now, the predominant approach to improving the performance of LLMs has been to increase the model size and invest in more computation during pre-training. However, this approach faces important limitations, such as the high cost of training and the need for substantial resources for execution, which may make its application unfeasible in resource-constrained environments, such as mobile devices or embedded systems. As an alternative, the study proposes intensive computation during inference to improve the accuracy of LLMs' responses in challenging scenarios. This strategy could allow the use of smaller models without sacrificing performance, achieving results comparable to those of larger and more expensive models. A central question of the study is, given a fixed computation limit during inference, how to maximize the performance of LLMs using different inference methods, and how effective are these methods compared to larger pre-trained models. One of the most popular methods for scheduling computation at test time is best-of-n sampling, where the model generates n outputs in parallel, selecting the best one as the final answer. However, there are other ways to optimize the use of computation at inference time. For example, instead of generating multiple answers simultaneously, the model can review and correct its answers in several sequential steps. Another approach is to fine-tune the verification mechanism that chooses the best fit answer. It is also possible to combine parallel and sequential sampling, along with different verification strategies and search algorithms, to create an even more robust inference optimization scenario. To define the optimal inference time strategy, the researchers introduced the concept of test time optimal computation scheduling strategy, which seeks to choose the right hyperparameters to maximize performance on a given prompt during inference. The researchers explored two main strategies to optimize inference time computation. The first focuses on modifying the distribution of proposals, adjusting the LLM to iteratively revise its answers in complex reasoning-based settings. The second strategy involves optimizing the verifier, the mechanism responsible for selecting the best answer from those generated, which can be improved through a reward model that evaluates the correctness of each step of the answer. To evaluate these approaches, experiments were performed on the Math Benchmark Challenge using PaLM-2 models. The results showed that the effectiveness of a given computation strategy at test time depends strongly on the type of problem at hand and the LLM basis used. For simpler problems where the LLM can already produce reasonable answers, allowing the model to refine its initial answer iteratively proved to be more effective than generating multiple samples in parallel. On the other hand, for more complex problems, which require exploration of different solution strategies, methods such as parallel resampling or tree search based on reward models were more efficient. These findings highlight the importance of adopting an adaptive, optimal computation scheduling strategy for inference, adjusting the approach according to the type of prompt in order to make the most of the available computational resources. By strategically allocating computation at test time, the researchers were able to significantly improve performance, outperforming the best n sampling baseline while using only about 25% of the computational resources. The researchers also investigated the potential of test-time computation as a substitute for additional pre-training. They compared the performance of a smaller model with more computation during inference to a 14x larger model with more pre-training. For easy and medium difficulty questions, the smaller model, using additional computation during inference, achieved comparable results to the larger pre-trained model. However, for more difficult questions, additional pre-training proved more effective, suggesting that the scalability of test-time computation may not be a complete substitute for pre-training in all cases. The study proposes future directions for research, such as exploring more complex strategies that combine different review and search techniques, as well as developing more efficient methods for estimating question difficulty. The researchers conclude that even with a relatively simple methodology, increasing computation at test time can be more advantageous than increasing pre-training, with even more improvements expected as inference strategies evolve. In the long term, this suggests a scenario where fewer compute resources are used during pre-training and more are applied during inference. Don't forget to subscribe to our channel, like the video, and share it with your friends. Your interactions mean a lot to us and help us grow. See you next time.